Ready? All right, so here we go. And I should begin by making sure you guys know the customers don't come in and ask, like, can you perform Ohm's law on my car? Okay, so doing this mathematical stuff is like, we're really just trying to make sure you understand how this system works and what the effect of more resistance would be, or what the effect of less resistance would be, or, you know, overall, like how the electricity functions. You're probably not going to do this math again, unless maybe you're, let's say you want to add a big light bar to your vehicle, and you're like, okay, if currently I have this style lights and I want to add this other LED light, and you can actually look at the resistance of your existing circuit and the resistance of your light bar, you can probably calculate how many amps would flow, and then you could determine whether or not it's going to overload the circuit, right? So if you have like a 10 amp circuit and you do your math and the circuit's now going to pull 12 amps, you'd know you can't do that, right? You know you can't just put the light bar in there and add a 15 amp fuse and leave the existing wiring that's good for 10 amps, right? So this would more be, if you're doing something custom, obviously electrical engineers would do a lot of this type of stuff. So mostly just bear with me. This is so you understand how electricity works, not so you become super proficient at doing the calculations, okay? So that's why it's Ohm's law. That's the law of how the electricity works, and there's calculations related to that. Ready? So here we go. For some reason, once this will work. All right, it's like we were talking about when we're diagnosing with electricity, you know, you can't just observe it. Like, for example, if you had a problem with brakes, like hydraulic brakes with brake fluid, if there's a leak, you can see that with your eyes. If there's a kink in the brake tubing, like the brake line, you can see that. You can also measure it. But with electricity, you can't see anything. So you can, by all means, look at the wires and you can get some clues. If your connections are corroded, you know, that's pretty good indication you have some resistance. But you don't want to just rely on that. So I see a lot of times when people are kind of unfamiliar or new, they'll get really obsessed with like, oh, I have an electrical problem. Let me look at the wires. Let me take the connectors apart. Let me look at things. Let me look. And that's good if you don't really know, but we're not really trying to do that for several reasons. Let's say it's one of those vehicles we talked about that may be bought back by the manufacturer, right? It has this once every few weeks, it has some electrical fault. That's very difficult to diagnose. And if you think disconnecting connectors and looking is going to locate it, probably not, because on that vehicle there's probably 200 connectors. A lot of the connectors will have nothing to do with the actual problem the vehicle has. So you can't rely on just your eyes. We're going to have to do a lot of measurement. You have to understand how it works. The other thing is, when you want to disconnect and look and visually inspect, you're disturbing the harness, right? So if it's an intermittent problem that's hard to duplicate, and then let's say you get lucky and you try to duplicate it and it's doing it right now, your best bet is really to do the measurement, to observe, to verify, to measure the fault, right? Let's make it really simple. If it's a light bulb that intermittently goes out, right? That's probably not what the customer's concern may be. It's probably more like a problem with an ECU dropping off the network or something a lot more difficult to observe, but the concept will be the same. If it's a light bulb that's intermittently going out, right? Let's say you're driving and the light bulb's good, and then all of a sudden, boom, the light bulb goes out. You'd be like, all right, now I can test it because the light bulb is out, right? If you go to the connector and you start moving it around and boom, it starts working, now you're kind of like, well, I'm not exactly sure what the issue is. To really verify what it is 100%, now you got to try to drive it and goof around with it again to get it to go out. So what we like to really do is just leave it undisturbed and take measurements. And so if you had, for example, high resistance in a connector and it wiggles just the right way, and boom, the light bulb goes out, and then you wiggle it, and the light bulb comes back on, you can probably generally tell like it's going to be in that connector. But if you were to measure it, and you were to see you had an excessive voltage drop or excessive resistance in that connector, you know exactly which wire, exactly what terminal, you know exactly what's wrong. You've taken a measurement, right? So when possible, we want to be 100% sure. We want to be able to prove the measurement. We want to be able to prove what the defect is with an actual measurement, okay? So that's how I want you guys to think about it. If it was more of a DIY class, what I would say is look for the signs, corrosion. Sometimes they turn kind of green. Rust is a form of corrosion, obviously. If you see a wire and it looks burned, like there's all these clues, but after the clues, you really have to know exactly how this system works. And so that's more what we're going to focus on, okay? But it's not to say that there's not value in the visual. It's just that the visual only gets you so far. All right, so when we talk about Ohm's law, you've actually heard this once, but now we're going to really dial in on it. So Ohm's law, essentially, if we were to sum it up, it's look what it says. It takes 1 volt, looking for my pointer, 1 volt to push 1 amp through 1 ohm of resistance. Okay, so that's what they observe in Ohm's law, is like every single time. If you have 1 volt and 1 ohm, you'll get 1 amp. If for some reason you were going at it a different way, and let's say for whatever reason you couldn't measure voltage, but you knew you had 1 ohm and you had 1 amp, you could therefore determine you must have 1 volt, because that formula is true for all 3 of those things. So as long as you have 2, you can calculate what the third is without actually measuring it, if that makes sense. Right, and so in some ways, you know, like a lot of technicians, even myself, I'd say like, whatever. You don't really need to perform Ohm's law in the customer's car. If you want to know what the voltage is, why are you going to calculate it? Just measure it. And I would agree. But at this stage, you're just really trying to understand how electricity works. And I find a lot of times people can tend to get a little backwards. And so we're going to go along with the math for now so that you understand it. And then after that, we probably won't do a whole lot of math. But for now, we will. And then if you remember, you know what voltage is, right? Think of it as like electrical pressure. All right, so that would mean there's an excess of electrons on one side of the circuit and like a shortage, there's a lot of room for them to move over to the other side, right? So if we stick with conventional, you have a whole bunch of extra electrons on the positive side, and they're all trying really hard to get to the negative side. And they'll try as hard as they can until the balance is equalized, if that makes sense, right? So if you start with a battery at 12.6 volts, what we're really measuring is we're measuring the electrical pressure difference between the positive and the negative. So if the positive has 12.6 and the negative has 0, there's a difference of 12.6 volts. Makes sense? And those electrons will try to flow until we're at 0, 0, you know, or if you were to look at a battery and you were to measure from the positive and negative and you were to get 0, it doesn't necessarily mean there's literally 0 volts. It means if your positive terminal and your negative terminal are on the battery and it reads 0 on your meter, that means there's no voltage difference, right? So just picture your meter as it tells you the difference in electrical pressure between the red lead and the black lead. That's what it's really looking at, okay? And then if you remember, what is resistance? Resistance is the physical restriction of the conductor. So that means like, that's the resistance of the electrons. For me, I like to a lot of times think of, like traffic. Like if you get on the freeway and it's wide open, you have very little resistance, you can go. Like a lot of cars can move out. Right? Makes sense? But if you have a whole bunch of obstructions, right? You have trees down, you have snow, you have potholes, you have all these things. That's adding resistance. That's going to make it harder and harder for the cars to go, right? It's kind of like how the electrons are. So if you have resistance in the conductor, it's going to resist the flow of electricity. That's increase in resistance. Cool. And then if you guys recall amps, that's literally just the number of electrons moving through the conductor. So I visualize that with like, I mean, you could visualize that with traffic too. It's the amount of cars going by on the road. Or sometimes I'll look at like water. If you have a lot of current flow, that's like a larger stream of water going by. If you have a little trickle, that would be very low flow, very low current flow. If you turn on the faucet just a little bit and there's just a drip, that'd be very low current. And if you turn on wide open and it's flying out, that'd be much higher current, right? So that's kind of visual. Now, a thing to remember in that calculation is if the pressure stays the same, but the restriction doubles, the amps will be reduced by half. So let me say that how I would say it. Your voltage stays the same, right? But if you double your resistance, your amperage will be half. See how there's like see how it's proportional there, like we mentioned a couple times? So if you had a circuit and you got 12 volt battery, maybe it's 12.6, but we'll say 12 to make easy math. That's generally what we're going to do. If you had 12 volts and you had a 4 ohm bulb and you added 4 ohms of unwanted resistance, you just doubled your resistance, right? Your amps are going to be half. See the relationship there? Your amps aren't going to double. Make sense? Your amps are going to be half. That's how the relationship is. Here's the visual again. You've seen this, right? So sometimes, honestly, if you really want to cheat on your ASE exam, get this tattooed on your forearm. They can't really get you in trouble for that. The people at the test center won't even know what that is, but you'd be like, oh, well, the ohms doubled, so that means we're pulling up on 2 ropes now. That means your amps are going to be halved, right? But you really don't, you can get this tattoo if you want, but by the time we're done with this lesson, you really shouldn't need the tattoo anymore. All right, so don't do anything until at least you give this lesson a shot. And also, I accept no liability if you do this and then you regret it, okay? All right, but if that's true, I could apply it a few different ways. What if, bear with me, what if the ohm started pulling only half as much? What do you think the amp would do? Exactly, correct. So see, you're starting to see this relationship. Now, for me, practically, I actually more visualize it like this. Like I don't really particularly care to get out and do the numbers. But I do want us to do that because that way you're going to see it will test out every time. It'll do exactly what this would show. And you can prove it mathematically. And then later in the, like probably next week, we're going to actually do that on the boards and you're going to take measurements and you'll be like, oh, this did exactly what I predicted it would do. Okay. So you'll learn to trust this scientific law. All right. So here's another thought. What if the volt started pushing twice as hard on the amp, but the ohm stayed the same? It'd still double the amps, right? So they all have an effect. There's like 3 different things to look at here. If you had double the volts, that's going to double your amps, assuming your ohm stayed the same. But what if you had half the volts and your ohm stayed the same? You'd have half the amps. Makes sense? Kind of interesting.
So you're only pushing it out quicker, you're not pushing more out?
It like the way that I think of it is sort of like if you just literally look at this exact image, if you started pushing half as hard, it's going to take longer in a way, right, to push this guy through. And you're going to be able to push less amps through because this is actually, picture like an electron, right? It's going to push an electron. But if you're pushing twice as hard, yeah, it's going to push more. Faster is probably accurate, actually. Now, I don't know about physically faster. Like, once you get into that, I'm sort of like, I don't really know. Like, I don't know if those. I think electrons move at a dedicated rate, and I think it's the speed of light. But that's where I run out. Like, if you want somebody to give you the real like super physics science version, I'm not the guy. but I can apply it really well. So if we look at this, let's apply this. What if we have, I don't know, what do you want to name this guy? Buddy? Hey, Buddy. If Buddy is pushing a wheelbarrow up a hill, the incline is going to be the resistance, right? And so if you've got more of an incline, it's going to, Buddy is going to have to, it's probably not going to move as many loads of the wheelbarrow, right? It's going to slow Buddy down a lot. Where if you have less of an incline or a shorter incline, Buddy can move so many wheelbarrows up that incline. That's like a little bit more of a physical representation. But what's interesting is like we mostly focus on the varying resistance, and for good reason. That's pretty much what happens in automotive. Like our voltage is generally consistent. We don't ever get in the car and start up and be like, oh, today my car decided to be a 24 volt system. It just doesn't work that way. It's 12 volts today. It's going to be 12 volts tomorrow. It was 12 volts yesterday. So generally our voltage is mostly the same. Our actual source of voltage being the battery, or if it's running, technically kind of the alternator, right? But we'll keep it simple at the battery. So we're mostly worried about the resistance that changes in the circuit because that's outside factors, corrosion, damaged wiring, mice chewed the wires, this types of thing. But likewise, if you think about it, if we were to get Buddy to get a helper, and now you got two buddies, you got double the force pushing up the same hill, can't you see how we'd move double the wheelbarrow loads, right? So like that's what I mean with electricity. To really understand it, you do have to understand we change more than just the resistance, even though in the automotive we're mostly looking at varying resistance. If you were to vary the voltage, it has an effect as well. All right, so like for example, when we go to measure it though, you can't see this. We're going to actually come over here and we can measure voltage drop. We're going to use our meter in all these different ways. So if we wanted to really analyze this circuit, we could actually measure what's our source voltage, and let's say the battery's 12.0. That's probably not accurate. If our battery is 12.0, then if you wanted, we could actually disconnect the circuit and measure the resistance through the switch, through the bulb into ground, and we get the ohms. And if the ohms was, let's just say 12 ohms, if I have 12 volts and 12 ohms, I know that I'm going to have, what's 12 divided by 12? That's going to be 1 amp. So I can do the math because I know the formula, and that's kind of where we're going with this, okay? So this is more applying it kind of in the same way. If the voltage is doubled and the resistance stays the same, the amps will be double. And like I was saying, usually when a circuit fails, it's because the current flow is too low or non-existent. So let me give you an example. The headlight bulb is out, completely an op. If the headlight bulb is not working at all, that's generally going to mean there's excessive resistance, probably a full-blown open, right? If it's an open circuit, the resistance is probably going to be OL, so we just generally call it an open. That's going to have 0 amps. There's going to be no flow. And it's kind of weird if you think about it, because if your resistance is infinity, your amperage would therefore have to be 0, right? So that's why OL makes a lot of sense to me as out of limits. It's kind of like infinite. All right, and that'd be if the bulb is out completely. So that we can already anticipate we're going to have excessive resistance, probably an open. But what if the bulb was dim? It'd be like, the bulb is dim. I think I'm going to have excessive resistance somewhere, but it's not going to be a full-blown open, right? I'm going to be, maybe looking for 10 ohms or 100 ohms of resistance, but probably not 100 mega ohms, which is millions, right? So we can measure that in several different ways, but let's start actually at the bottom. A resistance check of the electrical device would indicate high resistance or open, right? So if we think we have high resistance, we can measure that. And I agree with that. And that's a good experimental way, and that's a thing that we're going to do on the boards. but just don't get too attached to resistance, because when we measure resistance, you're measuring the circuit in its easiest state. So like the way that I've explained this in the past that I think will make sense to some of you, maybe not all of you, is like right now you're sitting, you're studying, you're listening. If you had a heart condition, do you think this easy task right here is going to bring it out? Because you're not working that hard, right? So when I decided I want to get out of the dealer and get into teaching, I really needed to take a job where I could work like a weird shift and then start to teach during the day. That's where all the teaching opportunities are. They're during the day. So I left the dealership and I went to work fleet at the railroad as like a diesel mechanic or machinist. But the thing is, the railroad's funny. If they hire you, they pretty much will not fire you. So they're very, very careful on who they hire. Right. Once you're in, it's sort of like you gotta do something really bad, and they gotta build a case to finally actually let you go. Right. So when I went to get hired, they had to have me do all these tests, and one of them's called a stress test. And I was like, well, you're not going to stress me out. And they're like, it has nothing to do with that. Get up on that treadmill, and you're going to run like at an incline really hard. And in the meantime, they have all these EKG things monitoring my heart. And I'm like, whatever, this is fine. And so I was thinking, like, why are they doing this? You guys tell me. Why do you think? Yeah, to really test your heart. Like, they don't, I mean, it sounds harsh, right? But they don't want to hire somebody who has a pre-existing heart condition and then employ them and then be like, hey, do this hard labor, and then, you know, have them have a heart attack, or have them be like, yeah, you hired me to do the job, but I can't really do it. So, you know, that, because again, they're not going to just fire you. They're going to be like, all right, well, we hired you, so now we have to like make a fake job for you to do so we can keep you employed. Like, it's just a big, it's a big company. They're kind of funny, right? And they have their own retirement system, so they're very careful who they bring on. So rather than just do like what you'd get on your physical, right? They check they listen to your heart, they check your blood pressure. They're checking all that stuff, but then they have you run as hard as you can, as fast as you can. Then they're like, we'll find out if you really have an issue. See what I'm saying? The test you do while you're sitting down, relaxed on your physical, that's the resistance test. It's a good test. It'll find some issues. But if you really want to test it, I would recommend a voltage drop test, because you're going to test the circuit while it's actually working. Make sense? You're going to test those wires while they're being forced to carry a bunch of current to light the light bulb. Make sense? So while we do these experiments, you're going to learn to love resistance, and it's nice. It's just once in a while, you're going to get something that's kind of weird. You're going to get a wire that's mostly broken, but it has a few strands, and a resistance test will pass it. But if you actually test it while it's carrying the current, while it's lighting the light bulb, voltage drop will fail it. And you'd be like, whoa, why did resistance pass it but voltage drop fail it? And it's because those 3 strands of wire out of the big bundle of 50, you know, in one wire, there's all these multiple strands wound in there, right? So if there's supposed to be 50, that's enough to carry all the current and not add a voltage drop. But if you have only 3 and you use your meter with your little 9-volt battery, it's going to be like, yeah, this is good. The electrons can make it through there. Yeah, but you're only sending a little tiny bit. And they're like, everything's fine. Once you try to carry 9 amps, all of a sudden it gets to that point and there's only 3 strands and the electrons are crowded into 3 tiny little lanes, and it gets hot, and next thing you know, there's a lot of resistance there, and now your bulb is glowing dim, and so there is resistance in the circuit, but your resistance test passed it. Your voltage drop test would have nailed that, would have found it. You'd be like, oh, there it is. All right, so that's real world experience, just letting you know why this is better. But how can voltage measurement indicate resistance? That's what Ohm's law is. That's why we're learning Ohm's law. Voltage drop will tell you what resistance is. Okay, we'll show you more. All right, so here's an example. Right here, we're looking at, this is the load device. So this should have the resistance. We can measure the resistance, but We can also calculate the resistance dynamically if we measure, the voltage and if we measure the amperage, okay? But for now, we're mostly just talking about this being the load. So generally, when we do our Ohm's law, we're just trying to determine what the load is. All this other stuff shouldn't really have much resistance, right? We should have very little to no resistance on the wire, on the terminal. The switch should have very little. The load should have whatever it's designed to have. The load should have resistance. That's why it does work, right? And then the ground should have very little resistance, right? Then if we were to, flip that over to voltage drop, you'll notice it's dropping 12.48 across the load, and it's dropping like almost nothing across this connection, this fuse, this wire, this switch, all that stuff. That's good. It shouldn't really be dropping a lot, but actually in this case, it's dropping a little too much. That's kind of the point of it is, we're going to tie Ohm's law to how we would diagnose this, and you'd understand why it's an issue. Cool. And also, this is about circuits too. So if we were to discuss, circuits are made up of the components and the interconnecting conductors. That's really just wires. We're pretty much using wires. Now, the reason we say it like that is because let's say you're looking at an electronic device. Sometimes they have printed circuit boards, and they're not wires. They're just like literal trails of almost like solder. It's like, imagine the 3D printers we saw, except they print a conductor and they can make a path for the electricity to go, like in an instrument panel or some sort of electronic device. So technically, that's not really a wire, but it's an interconnecting conductor. And again, we arrange them so we can control the electricity to perform a task. So with this one, we turn the switch on and off, and it makes the light bulb go on and off. How did we do it? It's really simple. We just pulled off the positive, sent it through a switch. After the switch, we went to a bulb. We're going to have the bulb do something. Like if we put the bulb in the front of the car, it's either to make it so we can see or make it so other people can see us. If it's an orange bulb, it's probably so other people can see us, especially if we're parking, or if it's on the side of the car so that people can see where the side of the car is so they don't hit you, right? But if it's a bright white bulb and it shines a beam, that's probably for us to see. That'd be like a headlight. Or if it's inside on the ceiling, that would be like your dome light or whatever. So essentially all the circuit is a way to control that light bulb so that light bulb can do what we want. Then you notice it just has to go to ground. So remember, ground always makes its way through the chassis all the way back to the negative terminal. So don't think that they just go die here. The electrons will go all the way back to the negative. I just want to remind you about that. Cool. So that's a good example of a simple circuit. And there's going to be several different types. Series, which is where we're mostly going to spend our time. And parallel. We're going to go into parallel, but I don't spend a ton of time on parallel, mainly because when you have a problem in a parallel circuit, the best way to troubleshoot it is to break it into multiple series circuits. So you have to know what to do to start, and then once you understand the parallel, you'd be like, all right, I'm just going to focus on this part of the circuit because I understand how it works, and then you're basically back to series. So series is about 3/4 of what we'll cover. And then parallel, and then it gets tied back to series. And then, of course, when we look at series parallel, that's just series parallel. You have to do almost nothing because you already know how both of them work. You just have to be able to combine them in your mind. Okay? Yeah, and we will cover these a little bit more later, too. So when you hear these terms and you're like, I didn't totally get that, it's okay. We're going to cover them again. All right, so a little more about Ohm's law. Remember, it's the relationship volts, amps, and ohms. And I kind of would like to make the formula V for volts, A for amps, and the omega symbol for ohms. But that's not really the industry standard. So when we get into this, you're going to see like VIR or EIR or, there's different... We're using different letters because it depends on whose perspective we're covering it, okay? So just bear with me on that. And I think you guys will see a lot of this is, you're just hearing it multiple times. The resistance stays the same, but the voltage rises. The greater force pushes more current through. Yeah, that's logical. So here is, let's get to application. V equals A times R. Say, what now? V is what? Voltage, yes, exactly. I like that one. V can sometimes be E, E being electromotive force. So you'll see, sometimes you'll notice it'll be E rather than V, and you're like, now I'm really confused. And I agree, it's kind of frustrating. A is, yeah, or amps. Yes, correct. And R gave you right off the bat as resistance, but I tend to like that as just the omega. Okay, so you guys are doing some good jobs taking some notes, but I think you'll find this summary more helpful than your notes. You ready? So let's do a little bit of this together. Let's say we know what the V is. What do you think the V is going to be in this example? We're gonna do this. We're gonna literally do this job together. I just got to grab this pen, this little tool here. Let me pick a color. How about, let's see what shows up good on the screen. How about this nice lime green thing? What do you think the V is going to be? Give you a clue. It's right there. All right. Where'd the V come from? Yeah, so it's whatever really like the system voltage is. You know what? That green is not a great choice. I thought it would be good. It's all right. I'm hesitant to do this, but I'm going to go with hot pink. Yeah, I think that works better. All right. And then, so you guys understand where we get the voltage from. You got to you'd probably measure it, to be honest, but if you're working with automotive, you know, we have a pretty known voltage that we run in our systems. And then what we need to also know is, let's go with ohms, because generally that's something. How would we know how many ohms are in this circuit? That's something that we probably would have to measure, actually. You know, I mean, we really should measure the voltage too, but let's just say if you measure the voltage and it's 12.0, and then you go ahead and you switch your meter over to ohms, and you disconnect it, and you actually measure the whole circuit, and it reads 4 ohms. If you know these two, you can determine the 3 amps, right? So the way that I was going to show you this, I'm going to see if I can do this okay. Yeah, I think we'll just cover it. All right, so if we're to do this, we know the 12, right? So we know the V, we know the R. So what don't we know? We'd actually just cover up the A because we don't know that. And what do you have left? V over R. So that gives us our formula. So the V was how much? 12, right? And the R was how much? 4, like this. So you're literally just doing this formula of 12. I dropped that pen. Bummer. Right here. 12. And then you're just going to do over 4. Doesn't that look like 12 divided by 4? And then you just make the equals right here. What's 12 divided by 4? Correct. It's that easy. So that's really what this says. But I believe it's on one of the next screens. I'm going to show you how to start doing these. But first, I'll clear all these drawings and pick up my regular pointer. And then I'm going to just kind of show you, like, this is how we would normally do it. And see, remember I told you they can switch it from V to E. But if you have this right here, and you know the thing that you don't have, you just cover it up. So let's say you don't have the R, You cover up the R, and you have what? E over I. So that's E divided by I.
It's just volts divided by amps.
And yes, volts divided by amps. Yes, correct. Or let's say that you don't have the E. Let's say you don't have the volts. You cover up the E, or the V, and now you have I next to R. That becomes a multiplication. Okay, so I'm going to actually make a little note about that. Okay, so if they're next to each other, it's not plus, it's multiply. I times R. All right. Or if you don't have the current, the I, it looks like you cover it up and it's E over R. So again, that's divided by E over R. All right, makes sense? So this one, even draw right here, E. That's a little tough to do off screen. I got a really good pen, but I can't do it on the second screen. E over I. Okay, and this one's, let's even switch it up. Let's say it's V over, I even would like to do omega, right? So if you can just remember this, you can very quickly calculate. And you'll see it's not really that hard. All right, so with that, you can consider drawing that little circle. Sometimes we draw it as a triangle too. I'm going to show you a few different ways. And that's kind of where we were going here. I'll summarize this for you. If you know V and R, then to find A is V divided by R, right? So this is one way to remember this. But my memory's not that great. I mostly put my effort into trying to understand it. So once I understood, I don't have to memorize 3 formulas. I have to just remember how to draw that little circle, EIR, or VA omega, VAR. I don't need to remember 3 things. I can remember 1. It's just easier for me. So if V and R are known, to find A, it's V divided by R. If V and A are known, R can be found by dividing V by A. If A and R are known, then V is found by multiplying A by R, right? So that's the long version of what I just showed you right there, which is, I think probably most of you are a little more similar to me. You're going to find this much easier. Right, this is how I would do it. All right, but don't just wait. There's more. We're going to actually do some calculations together. All right, so right here, let's draw in our letters. I'll walk you through one, and then we'll get them going together. So, do you guys want to go with? Let's go with V. And yeah, let's make this V, okay? Because I like V a little more than E. E is just electromotive force, which is, we measure it with volts, but, you know, V makes more sense to me. And this one's actually, these are switched, but it doesn't really make a difference. I never noticed that before. So this is ohms and this is amps. So this one is V. How can we figure it out? It's 4 times 6, right? That's just the way it's laid out. Does anybody know what? Okay. And it's okay if you had to use a calculator, that's fine. But yeah, if you do 6 times 4 comes up to 24. So according to Ohm's law, the V would have to be 24, right? Because Ohm's law says if we have 4 ohms of resistance and we're making 6 amps going through that 4 ohms, there has to be 24 volts pushing those amps. They're bound, right? They can't be like, well, today these electrons decided they're going to move different than yesterday. It doesn't work that way. Okay, cool? So now this one, I want you guys to just work on for a second. All right? We know the volts. We know the ohms, or the R. We don't know the amps. All right. I'm not going to say a word. I'm just going to start working it. All right, did anybody get a number other than 4? Your answer would be 4 amps. And if you were to do this on the boards, you'll find it's generally true, but there's one thing I have to warn you about. We are talking about the ohms right now. And what we learned in the theory was, remember, when things get hotter, what happens to their resistance? It goes up a little bit, yeah. So the thing is, when you measure the bulb, if the bulb is 3 ohms, by the time you actually get it hot, it might be 5 ohms or 10 ohms or something. So this is true. What we kind of would need to know is like, hey, how much resistance is there going to be in that filament when it's glowing red hot? And then you could get the exact amps, right? So we did a calculation based on maybe if it was just the cold resistance, whereas we need to do it with the hot resistance. And that's why when we do our experiments, you notice they may be like a little off. You'd be like, huh, did I just break Ohm's law? Like, no, not really. There's variation in temperature. All right. All right, that one was really easy, right? You guys thought this was going to be difficult math? No, it's not going to be difficult math. If it's difficult math, I wouldn't be the right guy for the job. Okay. All right. I'm going to give you, this is where we're going to do a few. I'm going to give you a few options. All right. How about, we'll keep it simple on this first one. I'm going to give you 12. I'm going to give you, here's a familiar one, 12. I'm going to let you work on it for a minute. And that's it. And I'll slowly start talking through it. I know V. I know R. I don't know A. So I cover A, which means it's going to be V over R equals, so it's going to be 12 over 12 equals 12 divided by 12 is 1. If you got 1 amp, you are correct. Very good. If you got a different number, well, let's try again, shall we? And if you're not grasping it yet, just write the whole thing out. Write it out all the way how we did it. All right, let's make our volts the same. 12. Remember how we had 6 ohms? Let's make we had 12 ohms. Let's make it half the ohms. 6 equals A. Now I just want to make a casual observation here. The voltage is the same. The resistance is half of what it was. So if you understood the relationship, you probably already have the answer based on the previous answer. Right? So we'll do the formula. V over R, so that's 12 over 6. 12 over 6 equals 12 divided by 6. It goes in there twice. Now wait a minute, is that interesting or what? If I did half the amps, what happened to my ohms? They doubled. Remember we said that that would happen. If you have half the resistance, twice as many electrons will go through. It's proportional. Cool. All right. Well, if that's true, how about, for whatever reason, we got half the volts. 6 volts and still 6 ohms. Oof, come on, baby. My goodness. Drop that. I dropped that pen. I was also thinking about duplicating screens for a moment. You know what? I'm actually going to try that. Let me try that real quick. That way I can use my pen. Temporarily, let's just do a duplicate. All right. Okay, we're still going to share screen 1, share. Keep, minimize. See, well, that might make it a little bit of a bummer, but that's okay. What did we say? We had 6. Ooh. Annotate, pen, 6 and 6. 6 divided by 6. How many amps do we have? Is that kind of weird or what? You have 6 volts now, but it still does 1 amp? Yeah, that's true, because you only have 6 ohms, right? So it's still proportional. It's still the same. What if we went back to, oh, I'll tell you what would be fun. What if we did a 24-volt system? Cool. And we kept our resistance at 6. So it'd be 24 divided by 6 equals. Isn't that interesting? So we've got 4 amps, and that's simply because we have basically double, right? If we had 12 volts and 6 ohms, we would have had 2 amps. But if we have 24 volts, that's double the push. I would expect to have it move double the amps, and therefore we do, right? So the math actually should kind of make logical sense, and it does. All right, but let's switch it up here. Maybe we don't know the volts. How about if we have, let's go with ohms of 6 ohms, and we have 2 amps. How would we figure that out? Well, that's how we look at this. It's R times A, right? You guys understand how we got that formula? We got that formula because we covered up the V. So we cover up the V, and you're looking at R times A. The R is 6. The A is 2, which means the answer is 12. Make sense? So it's a 12-volt system. It was pretty logical. All right, how about if we had, somehow it doubled. Let's say we used to have 2 amps, now we have 4 amps. If you're understanding Ohm's law, and I'm telling you your resistance is the same, but your amps just doubled, You pretty much should already know the answer, but I'm going to prove it to you mathematically. 6 times 4 equals what? So you must have a 24 volt push on that. If your amp's just doubled and your resistance is the same, clearly you got double the pressure. All right. Now, what if, let's just see if you guys are tracking with me well. What if I were to take that and I were to say, you know what? I no longer have 6 ohms. I'm going to make it 12 ohms. 12, but we still have 4 amps. I'm sorry, I did that different. R times A. Yes, that's correct. So let me visually explain. So we had a resistance of 6, and we doubled the resistance, but the amp stayed the same. Think about what the voltage would be. Right? If we doubled the amount of ohms, but it's still flowing the same amount, we must have doubled the volts as well. Make sense? So 12 times 4 is how much? 48. Or if we wanted to get really tricky, what if we didn't have 12 or 6, we only had 3 now. Let's say we only had 3 ohms and we still had 4 amps. That must not have that much voltage, because with only 3 ohms of resistance and still only making 4 amps, it must not have that much voltage. 3 times 4 would be, that's back to a 12 volt. And there's a little bit of a lesson there. One of the reasons we run into probably so many resistance problems in automotive, as you can see, we're running a 12 volt system. So if we have a 12 volt system, the amount of resistance has a really big effect to amperage, because we only have 12 volts, right? Imagine if you know these homes and buildings are running 120 volts or so. Imagine if we were running 120 volts in the vehicle. If there was a little tiny bit of corrosion on the connector, it wouldn't make that light bulb go dim. You'd have to actually have pretty substantial corrosion. So there's actually been pretty good discussion about, hey, why don't we increase the voltage in the automotive system? And there's a little bit of challenges with that. I mean, 12 volts is really safe. We've spent 100 years fine-tuning electronics for 12 volts and stuff. And so 12 volts is just what it is. It used to be 6 volts back in the day, but you can see there is some logic for why you would want to potentially increase the voltage. And when we do power calculations, I'll show you one more really good reason we may want to. All right, so how do you guys feel on these calculations? They're not that hard, right? Had enough of them? All right, no more calculations, they say. The people have spoken. Now what I got to do is I just got to flip it to multiple screens real quick. Which I can do. I got to get rid of annotate. Extend. Boom. Just like that. Keep. And we're going to share screen 2. That wasn't that hard, but was it a little fun? No, you hated it. Don't lie to me. I know you hated it. That's fine. We're going to do it anyway. All right, so now that we're in agreement on the Ohm's law calculations, let's get into power. And so you'll remember in the introduction part, I said, I don't really like to call voltage power because it's different. Like the power went through the switch is sort of like, but did it though? We're really measuring voltage. We're not measuring power. Now I think you'll understand what I was trying to say. So work is done when energy is released. I want you to keep that in mind. And energy is the potential to do work. And the difference between the electron supply at the battery terminals creates electrical force, which is called potential. Okay, now you're like, what? More terms? Voltage, potential, source. It's all the voltage difference across the battery. I like to just call it voltage, keep it simple, stupid. So if we're going to tap the potential, means we're going to convert it from one form to another. So if it's the battery's chemical energy being converted into electron flow, that's being converted into electrical energy. That's tapping it. We're actually doing work with that. And converting it is like an energy transformation. All right, so like the most fun version of energy transformation I can imagine is you put a certain amount of gas into a gas tank, and then you move that vehicle with an engine and all that type of stuff a quarter mile down the track, and you time how fast you can do it. That's actually doing work. That's a calculation of power, right? It's not really potential. You're actually measuring how much work was performed. And then we can assign a time to that as well. All right, so when we talk about that, check this formula, right? Power is the rate at which work is performed. Okay, so it's just a little different. In electrical circuit, power refers to the rate at which electrical energy is transformed into another kind of energy. So like, you know, if we think about, you know, engines, we really measure those generally in horsepower, which is fun and it's American stuff. But like electric motors, we actually measure those in horsepower too, but a lot of times we'll measure them in watts. So if you ever heard how many watts is that motor, watts is like just a measurement of power. All right, so 1 watt, interesting. 1 watt is produced when 1 volt causes 1 amp of current flow. So hold on, this is a little different though. This sounds like Ohm's law, right? But it's not. I mean, we're calculating power now. So it's not VIR or VAR or EIR, depending on the formula, right? It's P equals V times A. Power equals volts times amps. So remember I was saying there'd be some justification for increasing the automotive voltage a little higher because it would help to mitigate some of the corrosion or, you know, any unwanted resistance will have less of an effect if it was a higher voltage. Well, now I'm going to really trip you out. If we need things to do power is like work, right? It's volts times amps. If you have 12 volts and you need 12 watts, that means you would need 1 amp to do the work. But if you were to have 24 volts, you'd only need a half an amp to make a 12 watt. So you could actually lower the amps, which means you could run smaller wire, which means you could save weight and probably money on conductor sizes and space and everything. So don't be surprised. They already started doing this, and some of the, like a Tesla EV now runs like a 16 or 18 volt lithium battery. They don't have a 12 volt battery anymore. And that's probably some of the reason. Now, once you start to get into too high of a voltage though, that's when you need people who know a little bit more. So some of it's going to be a training challenge. And the other thing is, the higher your voltage is, the stronger your insulation has to be to make sure it doesn't arc out and push through the insulator, right? So just bear with me on that. If you keep this in mind, we're going to do some calculations on how to produce power. So if we have a 12 volt battery and it's moving 12 amps, it's moving 2 amps through a circuit, that can tell us how much power, how much work is being performed. All right, and here's how. This is the formula, P, A, and V. And if we look at this, we do the same way. What do we know? We know the V, We know the A. What we don't know is the P, so we would go ahead and just cover up the P. Let me grab my little bar here. Cover up the P. What do we have for A? That's 2. What do we have for V? That's 12. What's 12 times 2 is 24. So, right? So if we cover this up, it gives us the formula. It's A times V, which is 24. So we have a 24 watt. This is a 24 watt circuit. So if you hear the term watts, that's a measurement of power. And if it's in a 12 volt system, I mean, you can pretty quickly do it the other way around. I mean, if let's just say they said it was a 24 watt system, you knew it's an automotive 12 volt system, you could do 24 divided by 12 and be like, oh, that's pulling 2 amps. Part of the reason we want to do that is when we're trying to wire something custom, we need to know what wire size to run. They don't have wire for 24 watt power system. They have wire that's a gauge size that tells you how many amps it can handle. So if you know how much power that particular item is going to consume, and then you can determine the voltage, you can determine how many amps will actually be drawn through there, you can size the wire correctly, right? So that'd be more like what an electrical engineer would do. For us, generally we're not really doing the calculations, but you do have to understand, let's say you had a power window motor, and your power window motor was receiving low voltage. You were expecting to receive 12 volts, but let's just say you only receive 6. The formula would be 2 times 6, right? Now you only have 12 watts. What do you think that motor is going to sound, and what are you going to see? How are you going to know there's something wrong there? Slow and weak, exactly. Yes, correct. So when the motor's slow and weak, you're kind of like, I wonder if it's not getting full voltage. It's probably not getting full voltage due to unwanted resistance, right? Unwanted resistance is the number one thing we see. But now you can physically see why it would cause that motor to be weak. It's not getting the correct volts. Technically, it's not going to get the correct amps either. Volts and amps go together, right? So if you wanted to do more calculations, maybe we could throw a couple in there just for fun. Let's say you had a Power Wheels Jeep, or whatever the Power Wheels makes now, and let's say that those are run on 12 volts. And you're like, you know what? I want my kids to have the fastest Power Wheels on the block. So I'm going to take the 12 volt battery. I'm going to wire 4 12 volt batteries in series, and I'm going to make it a 48 volt battery on the Power Wheels. Now the amps, we'll just assume we're going to stay the same. But if we're to do the math like that, let me delete all these. Let's make this a 24, right? So I go ahead and I put in, no, I said a 48. Yeah, we want it to be fast, not kind of fast. Let's make this a 48. You see what I'm saying? 48. And if you're already looking at this, you can probably predict there's going to be a predictable outcome here. If it's 48 volts times 2 amps, what's our number? Okay, so you went from a 24 to a 96 watts. That's going to be nice. I bet you that's the Power Wheels I want to ride in if I can fit. It might look kind of silly, but I would do it. Okay, do you see how we made that Power Wheels faster? Because remember, watts is power. It's the ability to do work, right? So if it has more ability to do work, it's going to be faster. That's pretty much what we're trying to do when we're drag racing. Okay, now will the electronics of that equipment handle it? I doubt it. So that's kind of the problem, is when the system's designed for 12 volts, you can't just decide like, hey, I'm just going to give it 48 or 96 or whatever, make the number up, right? Because those electronics are designed to handle a certain amount of electrical pressure, certain amount of amps and stuff. But if you just look at it from a purely hypothetical standpoint, if you increase the volts or if you increase the amps, you increase the power. If you want to increase the volts, that electrical pressure is going to be hard to contain because it tries to push out, right? There's a lot more pressure, so you can't have your basic insulation. You got to have thicker insulation. So like, for example, on hybrid and EV, you know that they have the orange cables. That means like don't mess with that because that's high voltage. So 12 volts, it's no real harm to you, but a lot of hybrid and EV are running 200 something, some are on 400 volt. There are even some that are running 800 volt, but they mostly keep that isolated into the battery, you know. So when the voltage is that high, now you can see why, you know, people put $40,000 into their Corvette, and when they pull up next to me at the light in a Tesla, I'll just be like, hey, you want to do this? And just waste them with the groceries in the back. And the dog's still looking out the window the whole time, and they're like, what just happened? Because it's simple. With an electric motor, we can run super high voltage. And of course, there's advantages to electric as well. It makes instant power at 0 RPM. So like the Corvette's, you know, whining and grinding and, you know, it's starting to breathe and stuff, but the electric motor's just poof, it's just right now, you can have it. Now, yes, after a certain speed, that naturally aspirated is they'll run me down, but like from 0 to the posted speed limit, no chance. The all-wheel drive also helps, right? So if you can imagine when they started wanting to have these EVs be able to actually move the whole vehicle and especially move it quickly, their option is either A, jam tons of amps in there, which you can do, but amps are kind of hard to handle. That's talking about big conductors, right? Big wires. So instead, they're like, hey, you know what? Let's increase the voltage high, and we can get power out of it through high voltage. But then we're running big insulation and high voltage cables, and then we got to train the techs a little better and stuff, right? So even golf carts. Have you guys seen electric golf carts? Electric golf carts mostly are going to be like 36 volts or 48 volts. So they took the 12-volt batteries or 6-volt batteries, and they wire them up in series to get like a good voltage so that they can actually get pretty decent power to move that golf cart. Cool, so pretty fun. It's a good calculation to know. Will you do a whole lot with it? Probably not. But again, this is all about you understanding how electricity works and not being like, I don't know, it's a total mystery. It just never works the same. Like it does. It's always the same. You just got to actually know it. All right. Feel pretty good on those? Not bad. And so, again, you can apply that in multiple different ways. Depends on what you want to know. Most of the time, you know, we know the amps and the volts, so we're going to determine the power, so we can determine the watts from there. Same with solar and stuff like that, FYI. And then, you know, we just to add on that, like a lot of times we have to put a time to it. So when we talk about hybrid EV batteries, will be like, oh, it's 100 kilowatt hour. And then you're like, so that's not a measurement of power. That's more of a measurement of capacity. It can put out 100 kilowatts for an hour. Tells you how much electricity can flow out of that thing before it's dead. Not just an amount that can come out at one moment, but how long can it sustain 100 kilowatts for 1 hour? That's generally the standard with EV batteries is how many kilowatts per hour max. So if you had like a smaller EV, it might be like a 60 kilowatt hour. That means for 1 hour, it can put out 60,000 watts, kilowatts being 1,000. Or, you know, some of them are higher. Like that Hummer EV, that's eventually going to be mine, but I want to let it depreciate and have it break everybody's heart and get on a good deal. That thing's got like a 207 kilowatt hour battery. So it's the equivalent of a gas guzzler, but it's like an electricity guzzler. And for a while, people thought it was great. EVs were really good because they're like, hey, EVs are zero emissions. And then the Hummer can't, and they're like, never mind, we don't like EVs. That's a gas guzzler. But it's like, it doesn't use gas though. Like it was good, but now you don't like it anymore? It's kind of funny. I'd name a gigawatt. That's going to be the name. All right, so if we calculate it, now you guys can kind of see. Here's your formula. You could do it over and over again. And so you see it's a little different than Ohm's law, but it's Watt's law. Cool. Let's say this one, for example. We've got 12 volts at 5 amps. How would we determine how much power this bulb is? Well, we would do 12 volts, 5 amps, 12 times 5. We come up with 60 watts. Interesting. That's a 60 watt light bulb. So when you buy a 60 watt light bulb, you know, you're getting a measurement of power. A 60 watt light bulb, you're expecting a certain amount of light. And that's generally because technically, you know, that light's designed to really have a certain amount of resistance. And the resistance is actually going to control the amps if you think about it. But that's why it's a 60 watt bulb. 60 watt bulb should flow 5 amps.
If you change the wattage on the light bulb, does the system compensate for it?
No. It's a good point. So let's say you had a 60 watt bulb right here, and instead you wanted to put in a Silver Stars 90 watt bulb because you can't see. And rather than get glasses, you'd rather blind everybody. And you're going to run around with the super bright lights on high beams all the time. Very nice. Okay, how do they do that? Well, if you go from a 60 watt bulb to a 90 watt bulb, let's think about what the effect would have to be. We could actually do the math right here. If we had, right now in that example, and I actually encountered this, and it was a pretty good little lesson. I think I can keep this down here. We no longer have 60, right? We know that it's going to be a 90. All right, so if we know it's a 90, we know the system's a 12, right? So we do 90 over 12. Right, before it was 60 over 12, and that came out to 5. You understand how it was? It was a 90 because it was a 60 because it was 60 over 12. Now, if we know it's a 90, we actually have to do 90 divided by 12, and that math I'm actually not good enough at, so it's okay. I'll pull it up off screen. 90 divided by 12, we're going to get a 7.5 amp. So, does the system compensate? No. What was the effect of throwing the 90 watt Silver Star in there? If it increased the amps, that's interesting. And if it increases the amps within what the circuit can handle, no harm, no foul. But I've seen firsthand experience. Now, Sylvania makes Silver Star. It's a legit company. You know, they're good. I'm talking a little trash right here, but yeah. What I have seen in the past, though, is like they'll do the research and they'll say, yeah, if we bump it up to like a 90 watt rather than a 60, you know, you're still at 7.5 amps. That's still under like the 10 amp design or whatever. But I've seen in some cases where, yes, the wire, the fuse, everything can handle the Silver Star, but I've seen where the connection's a little loose at the bulb and the terminals don't fit it really tightly. And now with added amperage, a lot of times it can end up having a little resistance and get a little hotter there, right? So like the more amps we're going to flow, the more resistance there is going to actually make more heat. And so, you know, generally what we try to do from the repair side is just run the OEM equivalent, right? If you decide you're going to upgrade to a brighter bulb, look at how is it brighter. Is it brighter because it's more watts? Because that means it's going to flow more amps. What's the effect of more amps going to be? A little harder on the alternator, maybe a little harder on the circuit, you know.
So heating creates more resistance, or at least
both. They go together, right? And so if we were trying to pull 5 amps and there was just a little bit of a loose connection at the bulb, that's gonna make some heat. That's true. But the more amps you're trying to flow, the more heat there's going to be because it's going to become more and more resistance. And I've seen a lot of headlight connectors burned out by silver stars or something similar. And then the customers will come in, they'll say like, what do I do? And be like, you need to go back to OEM bulb, and now we need to splice a new connector on the end of it. And they're sort of like, well, I don't want to. And then be like, okay, then go, whatever you got to do. But, I can appreciate the brighter bulbs, but in my line is sort of like the cars can't come back with problems as a result of what I did, because then I got to pay. And I'm just not really down for that. So I'll give you one interesting idea, though. And that's not to say you shouldn't do it. It's just to say do it at your own risk. Like, you're changing the amount of current flow if the wattage is different. Now, if they have a bulb, let's say it happens to be an LED, and they're like, hey, look, we can make your 60-watt bulb have the output of a 90-watt bulb, but we can have your amperage actually be lower at 1 amp, I'm interested. Because it's like there's no negative to lower in the amperage. You're using less electricity out of the alternator, less stress on the switch, everything, but you're getting more light. Like, how is that? Well, I mean, LEDs are just a better, newer technology. Now, there's a bit of a negative. The LED, a lot of times they have to come with a little fan to cool them. Other times they come with heat sinks and stuff like that. So if it were me and the bulbs weren't bright enough, I'd probably lean towards an LED, simply because it's going to lower your amps. And to me, the less amps, the better. Like, the less amps we can flow, the better. It's just more efficient and everything. So all my stuff that I want brighter bulbs have LEDs. Right? Cool lesson. So if you think about that, if the LED has less amps, therefore the LED must have much higher resistance, and they do. FYI. All right, that's pretty good for our application of that. Let's see, I just gotta get rid of my pen. It thinks I'm still trying to draw. No more drawing. All right, I think we're probably pretty good on, let's do one calculation together. Let's do, how about a voltage of, you guys will see this is practically the same as Ohm's law, it's just a different formula. Let's do 12 volts and 10 amps. So you'd cover the P, you'd end up with A and V, so it'd be 10 times 12. Anybody can do that math? 120 watts. All right, that's a pretty substantial power supply. That's, in automotive, we don't, like, most of our wires are good for maybe 10 or 15 amps. Like, if you go to buy lights that are going to be more than 120 watts, you're going to have to run standalone separate wiring just for those, which is fine. You can do that, but just let you know. All right, now you really want to be tripped out? Remember I mentioned I was on the railroad, we'd have to do stuff with those diesel electric locomotives. When we would load test the main generators on those, we'd be running 2,000 volts. I tried to make that a comma. 2,000 volts at 1,000 amps. So what do you think that number is? Pretty big numbers. So it's going to be hard for me to draw all those zeros.
It is 0 or 2 million.
It is 2 million, correct. 2 million watts. So not a little m, but a big M. So some of the, in automotive, we're talking about, I've got like a 120 amp alternator. And you're like, how many, if it's a 120 amp alternator at 12 volts, how many watts would that be? 120 amp at 12 volts would be like, oh, cool, that's 1,440 watts. Then I get on a locomotive and at wide open throttle under full load, it's like 2 million watts. So that can power like a small town, not a city, but a small town. So when you see those things, that's the reason they can pull that massive amount of cargo. There's no transmission, there's no gears, there's no none of that. There's a big engine running a big generator, and the big generator directly powers a bunch of motors underneath at, potentially a couple million watts. So pretty fun. And you're not allowed to really be touching anything during that. You have to be in the cab, like just monitoring it remotely, making sure everything works. So FYI, don't play around. Very nice, very fun. Okay, so there's lots of power calculations for you. Now you know how to do that. Okay, let me pick this up and X this out. Okay, good. All right, now we're going to be into circuits, okay? So what we just learned is good, but we're going to start to understand how to apply it in the specific circuits. And to be honest, this part's, I think, is a little bit more fun, but it's also really critical that you are able to start to make the connections. All right, so in a series circuit, there's only one path, so that's why it's a series circuit. One path for current to flow. It's kind of like being on a single lane road. All the cars have to go all together. That also kind of means like they're all going the same speed too. That's kind of the frustrating part. So there's a specified number of cars, everybody moves together, they all have to go through the same obstacles, right? All the electrons flow at the same rate throughout all parts of the circuit. Cool? So if you were to start measuring cars going by this road, if there's only one way in and one way out, you know they all have to pass you. So you could take a current measurement at any point and it'll be the same. Make sense? Because they all have to go through that part. All right, so what that looks like in a diagram form. Here's a series circuit. Electrons come out of the battery. They go through the fuse. They go through the switch. The switch is closed. There should be current flow. Down here, this circle right here, this is meant to indicate like an ammeter. An ammeter is a tool where we can measure the current flow. To measure the current flow, we have to actually break the circuit open, send them through our meter, and then let them go back out our meter and continue on. Okay, so it's like an electron counter. It's like if the road's going like this, we're going to basically divert it and send them through here so we can count them and then send them back out. So you picture some little, like a little, like let's say almost like a toll booth. It's a person at a toll booth, like 1, 2, 3, 4, like that. But you have to actually send them through there to measure it, okay? So they measured 1 amp right here. Then right here, this meter is doing something different. This is designed to be a voltmeter, so we're actually showing how many volts drop. For right now, let's focus on the amps. We'll come back to the volts. Right, so there's 1 amp. The electrons go through the first bulb. There's still 1 amp. The electrons go through the second bulb. There's still 1 amp. Do you see how the amperage was the same all the way through the circuit? Because it's only one path. It's going to be the same everywhere. So the amps are the same, but you'll notice the volts were not the same. And this is where it can start to get just a bit confusing. So the reason why, I'm going to explain it a couple ways. We have 12 volts in a series circuit, like with basically any circuit. By the time the circuit's complete, and this is a complete circuit, right? It goes through a closed switch, and then it goes through the loads, and it goes to ground, and the ground is connected to the chassis, and the chassis connects it back to the battery. By the time the electrons go through a complete circuit, all the voltage will be used up. Okay, so you got to remember that. All the voltage. Well, what did we start with? 12. So all the voltage will be used up. Now, who should be using up the voltage? Only the loads, okay? The loads should use the voltage. The loads are the ones who do the work. Now, technically, do you think we might use a tiny bit of voltage like on a switch or a connector? A tiny bit, yes, I'll give you that. But for now, we're gonna kind of like say that's basically nothing, and we're just gonna focus on the actual loads. Why do you think This one used up 3 volts, and this one used up 9. I thought that they would have taken 6 and 6.
Resistance is lower.
Yeah, that's correct. So I start with this one because I don't want you to be too complacent and think that they're going to share, right? At this point, this is where I like to explain it. It reminds me a lot of siblings. I think I told you this. If the parents passed out $12 for allowance and you had 2 siblings of equal size and strength and they're going to fight it out, they're probably going to end up with about $6 because they're equally strong siblings. But in this case, if you look, this one's only a 3 ohm sibling. And this one's a 9 ohm sibling. So if this one here is 3 times larger than this one, it's probably going to get about 3 times more money. Make sense? Well, look what happened. This sibling got $3 because it was a 3 ohm resistor. That's like let's call that a 30-pound sibling. This one got $9 because this is a much larger, 3 times larger sibling at 90 pounds. That's the way that I visualize this, is they're going to consume voltage that's proportional to their resistance. And their resistance to me is kind of like their size and strength. The bigger a resistor is, the stronger it is. The higher the ohms are, the more voltage it consumes. Kind of make sense? So in this case, it has nothing to do with this one being first or last. But this 3 ohm consumed 3 volts and this 9 ohm consumed 9 volts. And that happens to be beautiful math because 9 plus 3 equals how much? 12. So the reason it's really easy math because we started with 12 volts and we have 12 ohms, so we have 1 amp. So this is just a beautiful way to illustrate the relationship. Now over here, what happens? We switched big sibling with little sibling. And if you thought it was going to change who consumed the amount of voltage, it doesn't. It doesn't matter where they are in the circuit. It just matters their resistance. That's how much they're going to consume. Okay, so we had 12 volts. We know we have 1 amp. And we can therefore determine that we have 12 ohms. And we could have done that by just looking at 9 plus 3 is 12. Well, the first sibling is going to take the 9. Not because it's in a different spot, but because it has 9 ohms. And the second sibling is going to get 3 because it has 3 ohms. And that's just the way it's going to be. All right. Now, what would be crazy is, what if we threw in another sibling right there? Now you got to split that allowance 3 ways. And so they're all going to get less volts. That's just the way it's going to be. But how much volts would they get each? Well, it depends on the size of the new additional sibling. Makes sense? And, we could do some examples like that, but does that so far kind of make sense? Because we're going to have to do some experiments to make sure it does. Now, let's say I made this more practical. Let's just say, see this 9 ohm bulb? Let's say it wasn't a bulb. Let's say it was just 9 ohms of unwanted, undesired corrosion resistance. Make sense? Look at the first bulb. The first bulb is dim. Can you tell it's just barely lit? And the second bulb is consuming all the voltage, so it's much brighter, right? It's getting paid a lot more. What if this wasn't a bulb and it was just that unwanted dirty resistance? What would happen to the first bulb? It would be dim, but you'd have no idea why. See, so remember in the beginning I told you if there's a dim bulb, I already diagnosed in my mind it's got unwanted resistance somewhere, right? In this case, it has unwanted resistance somewhere because it has a second bulb added in, and that'd be very easy to see because it's glowing in your face. But if it's corrosion, it doesn't glow and shine in your face. You're just like, why is the bulb dim? I don't know. And then you could measure and be like, why is the bulb only consuming 3 volts? And I'd say, because there's like 9 ohms of corrosion in the circuit that's consuming 9 volts somewhere, but I don't know where. We got to measure that. So what'd be crazy is if you just ignored this bulb and you did these measurements, and this bulb right here dropped 3 volts and this bulb right here dropped 9, you could therefore, using your voltage drop, determine that there's 9 ohms of unwanted resistance right there. And you'd be like, oh, I need to do a whatever, wire repair, replace a terminal that's loose, replace, a switch, something. Okay, that's where we're really trying to go. At that point, it's unseen. You have to measure it. You can't just look at it and only do what you see. Your eyes aren't going to be enough. Cool. So that's this is the words of what we just saw. In a series circuit, there's more than one resistance. Those resistances are connected one after the other. They're in a series, right? The electrons have to go through both, so one affects the other. And the total resistance in the circuit is the sum of all the individual resistances. What's that mean? What's the total resistance in this circuit? Do you see that right here? 12 ohms. How did we come up with 12? It's the sum of all of them, right? 3 plus 9. You got to add up all the resistances, and that'll give you the total. Okay, makes sense? And then the voltage at different points is going to change. And at each point where current flows through a resistance, a voltage drop occurs. A drop in voltage or a voltage drop, it's the same thing. Right? So if we back that up, current was flowing and there was resistance here. Would you agree? How much? All right, so therefore there's going to be a voltage drop. That's the law. This is telling us the laws, and this is showing us what it does. So if there was resistance here, it's going to drop voltage. In this case, it was a beautiful example. 3 ohms of resistance is going to drop 3 volts. 9 ohms of resistance is going to drop 9 volts. It's just the way it is. It's going to drop the full voltage, and it's going to drop it proportional to the amount of resistance throughout the circuit. Okay? And then voltage drop it's a good thing, right? When they occur inside of an intended load, okay? So right here, these voltage drops are good. We wanted these voltage drops because there's bulbs there. But what if we had, like I was saying, what if this wasn't a bulb? What if this was a connector with a bunch of corrosion in it? That'd be unwanted. That'd be bad. That would make our bulb dim, and you'd be like, it's acting like it's got a second bulb in there. Well, yeah, it's an unwanted voltage drop. It's an unwanted resistance. So we learn a lot on these boards using multiple bulbs that kind of simulate unwanted resistance. It's hard to really duplicate unwanted resistance because it would take time. You'd have to get some connectors to put on these boards, and then I'd go leave them out all winter long and then bring them back in and be like, perfect. And then it would make a bad unwanted resistance, but then by the time you disconnect and reconnect it 100 times, it'd probably clean the rust off, and then it'd be like, it's time to leave them out in the rain again or something, right? So we'll use the bulb a lot of times as a way that you can understand what an added resistor will do to the circuit. Okay, cool? So how about this one, for example? We can actually do Ohm's law on this one. If you look, we got a 12-volt battery, right? We knew we were going to have a 12-volt battery. That's pretty much what we always have. The 12-volt battery goes through, we could do it this way. Let's make it it's going counterclockwise. Goes through the switch, goes through a resistor, 4 ohms, through a resistor, 4 ohms, through a resistor, 4 ohms. What's my total resistance then? Okay, so we know it's a 12-volt battery. We know it's a 12-ohm total resistance. So we should be able to determine the amps. 12 divided by 12 is 1 amp. Yeah, exactly. Correct. All right.
Each of those resistors would have a 4-volt drop.
Correct. Yeah, it's proportional. 4, 4, and 4. Now, and that's how this circuit's designed. Now, a lot of times in the field, it's like you had a 4-ohm bulb, and then you had another unwanted resistance that's like some random number. Like, it's so rare to see it so equal and beautiful. You'd be like, hey, I've got a 4-ohm bulb, but then I've got like 197 ohms of corrosion resistance or something, some weird number. But yeah, that's exactly right. Now, if we were to add more resistance, and let's say end up with another 12 ohms of resistance, and it was 24 ohms of resistance, what would the amps be? Wouldn't be 1 ohm anymore. If you double the resistance, your amps are going to be half, right? It's always that relationship. All right, good. So now more on circuits. In the circuit, we talk about the fuse a bit already. The fuse is known as the protection device, and you guys understand why, correct? When we wire this up, these are our conductors. Those wires have to be sized appropriately to be able to handle all the current that needs to go through them, right? So if they design that, whatever, 120 watt powered bulb or heater or whatever, if it's 120 watts at 12 volts, it means it's going to have 10 amps. We need to have a wire that can handle at least 10 amps. They probably won't use a wire that'll handle 10. They'll probably use a wire that'll handle 12. Or the engineers are going to build a little bit of a safety measure in, but they're not going to use a wire that's going to handle 17, because if they're using a wire that handles 17, they're spending more money. That's more weight. It's not really efficient to be profitable. Okay, so they're gonna calculate how many amps, and they're gonna go up to just the next size, but not all the way to the next size where you can throw a 15 amp fuse in there. If it's got a 10, it's a 10. That's it. The wire may be able to handle a 12, but it's not enough to handle a full 15 or a 20 or whatever. That's just the way they do it. So the purpose of the fuse, if the fuse is 10 amps, but the wire can handle 12, the wire should never be damaged or get too hot or catch on fire, right? That's its job. That's it. Now the control device in this case is a switch, which is pretty typical. Why do you think it's the control device? Yeah, I mean, that's how we turn it on and off. We want to control the circuit, right? If it's the control to these lights in this classroom is that switch over there. That's normal. That's how we do it. Now, in this diagram, what is the load? The bulb. The load could also be, remember, we looked at the motor, we looked at magnetism of a relay or a solenoid or, all that type of stuff, a fuel pump or something. But in this case, it's just the bulb. Generally, we're going to focus on the load being the bulb, but just understand when you get into other subjects, the load is not always going to be a bulb. It's going to be something that's supposed to do work, remember? But that's the thing that we're there for. Like, actually, here's a load right here. A horn. The horn would be the load in the horn circuit. All the voltage should drop here. We shouldn't have voltage dropping here and not giving this enough voltage, because then this is going to glow dimly. Wait a minute, this doesn't glow. What do you think it would do? Yeah, it wouldn't sound right. You'd be like, oh, my horn sounds sad and weak. You'd be like, oh, it's probably got a voltage drop, an unwanted resistance in the circuit. And so you're diagnosing very much the same as a bulb, except it could be the horn or something. Cool. And then you guys understand the ground, the chassis ground, the chassis ground. You can see it again and again. Okay, and then so a little bit more about the circuits. So we talked a lot about how the series circuit works. Everything has to go through the series circuit. So the voltage is going to be shared through any of the voltage, through any of the loads or the resistance, right? Current flow will be the same. Then this is Kirchhoff's law, is the applied voltage is equal to the sum of the individual voltage drops. All right, let me explain what that means, Kirchhoff's law. If you looked here, if your source is 12, and then you were to add how much voltage dropped at each thing, 0.1 at the fuse, 0.1 at the switch, 4.7 at the dimmer, 7.0 at the lamp, the load, 0.1 on the ground, do you know what that total will be? Exactly. So Kirchhoff's law just says every voltage drop added up will always drop the full source. It's just the way it is. If it starts at 12, it'll be at 0 at the end, and it may drop it all on the load. It may drop a little here, a little here, a little here, a little here, whatever, but It's never just mysteriously disappearing or doing its own thing. We don't have like rogue electrons that are just different. It's not how it works. And so that's kind of what it's saying. The total circuit resistance is equal to the sum of the individuals. We just showed that, right? And then this is the thing with Ohm's law. If you think of it as how the system works and how it's predictable, you can most likely understand what you need to do to diagnose and repair it, right? So if we were to look at this, we've got a fuse, we've got the switch. Let's just say I had a problem with both of these two bulbs. Is it likely that I have two blown bulbs? Or is it more likely that I may have a problem somewhere with one of these components? Right? Like, so just understanding an unwanted resistance will have an effect. If the bulbs are blown, that would be reason for them not to work. But if we had a bunch of resistance up here, it would make both the bulbs not work, but the bulbs aren't bad, which is why I said, like in the beginning, when you have a car and you don't know what you're doing and the light bulb doesn't work, you put a new light bulb in there. And it does fix it a lot of times because the main failure point's in the filament. But you know, as a professional, if they're bringing it to you and they're going to pay your diagnostic time, they probably already tried to throw bulbs in there. So you're probably going to look at it and be like, you can look at the bulb and see if the filament's good, but on new stuff, it's an LED, you can't see. You look at it and you're like, is the LED good? I don't know. There's nothing to see. So what we'd probably really do is analyze the circuit and be like, do I think I have two bad LEDs? Or might I have a bad switch? And you just understand the relationship here is if you have excessive voltage drop right here, it'll consume all the voltage, it'll leave no voltage for these two, and they just won't work. Right? So we could have an open over here or a high resistance here or something. So applying Ohm's law to the car a lot of times just keeps your diagnostic path straight. It doesn't get you off task, right? You'd be like, oh, if these don't work, maybe it's because the battery's got a problem. Like the battery powers all the whole rest of the car. Like you got to understand how the circuit really works. All right, good. So let's say we look at this for just a moment. And I want to explain what we did here. We calculated the voltage drop across each of these points, and we could total them up. But a lot of times, that's not really what we're going to do if we're trying to fix the car. Right here, this is a good experiment to show you how it works. How I would probably proceed on this one, let's just say we had the lamp, and the lamp was dim. I might go right to the lamp and measure how much the lamp is dropping. And if the lamp is dropping 7 volts, and I was expecting the lamp to drop 12, what's that tell me is going on in that circuit? There's some resistance, actually not necessarily before. That's what's interesting. If the resistance is after, it would still only drop 7. So whether the 4.7 unwanted is here or there or here or here or here or here, it's interesting. The lamp will still only drop 7. Because remember that previous page where you saw we moved the 9 in front of and behind, it didn't make a difference. It still dropped 9 and the other one still dropped 3. So where the resistance is in the circuit doesn't change how much it drops. Now, there's another way that we could have gone about that. But if we just measure the voltage drop of the bulb and it's 7, and then I go and I measure the voltage drop of the dimmer and it's 4.7 and it was supposed to be 0.1, I'm like, boom, there's my problem.
So what you're saying is, regardless where it is, whatever resistance there is, we'll always take that exact amount.
Yeah, exactly. So people get tripped up a lot because we focus on it's got to be losing power, right? But power is that's why I didn't love to use the term power, but it could be on the ground. A lot of times it is on the ground, especially on the ASE. The ASE loves to have ground defects because it trips people up. If you had a 4.7 volt drop right here, right there, it would still only allow this to drop 7, and people are like, what? It's just how it works, right? We proved that. We proved it right here. This one only consumed 3. And you're like, well, is it because there's 9 over here or over here? You don't know yet, right? And then we switched them, and it still only dropped 3, even though the 9 was before it. Whether the 9's before or after, it's still only going to drop 3. It's pretty interesting. Now, there's another way we can test that, though, and this is what I'm about to show you. The way I would proceed in that case, if I wanted to know, I would do a different test. I would throw my ground lead and on chassis ground, and I would do what's called available voltage, which is different. At this point, I'm just probing my red lead along the circuit and measuring what the voltage is. So we started with 12, right? Then I move my red lead down after the fuse, and it's 11.9. If it went from 12 to 11.9, what was the voltage drop? 0.1. Hold that thought. Back here, we measured voltage drop with the red lead here and the black lead here, and it told me 0.1. Do you see how those are the same? But this tells you a little bit more, in my opinion. If I had 12 and now I have 11.9, I know my fuse dropped 0.1, but I also know I still have 11.9. Whereas with this one, I knew my fuse dropped 0.1, but see, I'm not actually guaranteed that I have 11.9 right here, which is why once I get in a circuit and I have a problem, I like to do this method, right? So if I had 11.9 and then went to 11.8, I dropped another 0.1. Then if I went across the dimmer and I had 7.1 after, I went from 11.8 to 7.1, that tells me I'm losing a bunch of voltage before the load, before the bulb, right? Whereas if I go to the bulb, before the bulb I have 7.1, and after the bulb I have 0.1, it tells me the problem's not down here. It tells me I've already lost too much going into the bulb because I only have 7.1 volts going into the bulb. See, so the voltage drop is great. And in some ways, it's easier because you don't have to stretch your leads across the whole vehicle. You can keep them nice and tight. Like I like to joke around, it's like T-Rex arms. If you want to do voltage drops, you could do them like this. Whereas if you want to measure available, you may have to stretch them out. But if you get a voltage drop and it's wrong, like this one is a 7-volt voltage drop, that's wrong, then you might go to available and you could be like, well, how much is coming in? Oh, I only have 7.1 coming in. That means it's before. Or alternatively, if we have 12 coming in and 7.1 going out, that means something after the fact is demanding that 7.1. So that's how I would know it'd be on like the ground side. Right, but it's a lot to eat on the first lesson about circuits, so don't worry, we're going to cover it a couple times. Cool, but so far it kind of makes sense. So this is a voltage drop, T-Rex arms, and this is available voltage where you're probing at multiple points. If anybody's old school and used a test light, this is what a test light did. A test light, you'd clip this bottom to the ground, and you'd go and you poke your little light here, and you'd see, is it bright, is it bright, is it bright, is it bright? Oh, it got dim. So it was bright here, it was dim here, something's wrong. See, so the problem with a test light is it doesn't give you a number. There's some advantages, I'll admit, but it doesn't give you a number, so you're like, hey, what was the voltage drop? And you're like, dim? You're like, yeah, how many volts though? And you're like, well, I don't know. It could be like 6 or something, like, you know, so that's not what you want to go into court with. Makes sense? It's not going to go well. So we're going to use the DMM, and we'll talk a lot more about the DMM, because the DMM can actually give us a pressure measurement, a voltage measurement. All right, cool. That's your first exposure. Not the last time you're going to hear it, I promise you. Okay, and then the other thing that we're going to work on, you don't have voltage drop or available voltage skills yet. That's going to take time. The other thing you need to work on is being able to predict what it should have. That also takes time. But because I'm introducing you to circuits, I need you to understand why you need to know what I'm going to be showing you in the next month. Sure.
When you're doing DMM measurements like that, you said you go and tap the red one if you have the chassis ground.
Sure.
How far is that chassis ground going to be?
Depends. So like, let's say I'm working in the interior. My favorite spot to pick up a ground is the striker where the door latch closes, because that one's always shiny, it's always grounded. It could be right there. If you're in the trunk, A lot of times it's all covered up with carpet and paneling. Sometimes we got to pop a couple clips out and like find a little bolt or something. So it's all about how resourceful you are. It could be kind of far, but as long as it's an actual good ground, it's a lot of times it's close. If it's a boat or if it's like a boat, a fiberglass boat, it's back at the battery. It's a nightmare. Cars are pretty metal though, so you could probably find one.
Do you have to have like an alligator?
I like that. That's the best way. Yeah, I mean, like if I'm trying to do something quick, I'll just push it pretty hard on the bolt and I'll push the other one on the load. But like, everybody's gonna need to have alligator clips because there's gonna be a time where you can't do both at the same time, and it just makes more sense to have alligator clip. It's a good one for sure. And then the other thing is, they do make lead extensions that roll up in a little spool. And sometimes if I'm struggling to find a chassis ground, I'll just bust out the extensions and I'll stretch them out. I'll go boom right to the battery, and then I've got my ground anywhere and I don't have to take clips out and find it and stuff. So some different options. We will do that on the car. Okay, I'm going to give you just a mini lesson in predicting. Now, based on what we measured earlier, you should know because I showed you the measurements, but where you need to be by the end is be able to look at this diagram and know what the voltage should be, and you're going to need to be able to trace it. So if we start with 12 volts, it goes across the fuse, we shouldn't drop much. That should be like red. So I'll even do the trace just for the first time. If it's what we would call like a source voltage, this should be red. Go through the fuse, it should still be red. Now, if the switch is open, the red's going to stop right there. But if the switch is closed, the red's going to continue. Now, when it goes to load 1, it's no longer really true like source voltage. We change it to what we call an in-between voltage, which is kind of frustrating. Let's make that blue. So an in-between voltage means it's not 12, but it's not ground. And the reason why this has an in-between voltage is because this has multiple loads in the circuit, which is not real common, but it can happen. All right, and I actually went just a bit too far. After the final load is where it should be green. And so I know after that it should be 0 volts, that's ground, right? So when you try to do diagnosing, you need to be able to trace these. And when you start, you really want to do that to learn it. And then eventually someday you'd be like taking your training wheels off. You're like, I don't really need to trace it. I can look at it and know what that voltage should be. And you should be able to do the measurement on the car and determine the issue. But starting off, it's really easy to be wrong. And then if in your mind you didn't trace it right and you do a measurement and you're like, oh yeah, there's 12 volts here and there should be, but there should have been 7.1 volts. You're thinking something's good when it's bad. You're misdiagnosing, right? So we'll cover circuit tracing. You're just not quite ready for that, and that's fine. But you will be, okay? So just to understand, really to diagnose this circuit, you got quite a few more things you need to know, which is normal, all right? And then with regard to measuring, we talked about measuring voltage, right? With regard to measuring current, remember I explained, if you want to measure current, you have to break the circuit open, send it through the meter, that's like the little toll booth, and the meter has to count the amps, and then the amps have to go through. It's very important right here that you understand you have to set your meter up to do this measurement, and we are going to, I have a whole thing on DMM use, but if you have your meter set up wrong, you can have this unfused, and that's bad for the meter. But if you move this lead to the big A that's got a 10 amp internal fuse, the circuit's protected, your meter is going to be protected, everything's great. The negative is if it flows over 10 amps, it'll blow the fuse in the meter, which isn't, at least it's a fuse, not the meter, but it's a $10 fuse. And you got to disassemble the meter to replace it. So when we go to do this, just make sure you have it right. Okay, and we will cover DMM use a little bit more, but just to give you a sense of if you did want to measure amps, this is how we do it. Break it open, send it through. Test it dynamically. Mm-hmm.
How would you break the circuit?
On the testers, you're just going to literally disconnect something, put your meter in, and then put your meter in what you disconnected and just loop it through. On the car, I'll be honest, this can be a pain. If it's one single connector with one terminal in it, no problem. If it's a fuse, even better. You can take the fuse out, you have an adapter, it'll pick up where the one leg came in and send it through the meter and put it right back out. If it's a big, huge connector, you got to disconnect the big connector and then you got to jumper each of the individual wires and then pick up yours and run it into your meter and your other meter. They kind of suck. A lot of times we'll chicken out on that and we'll just try to do like an inductive measurement because inductive will get us close. But if you had to actually get a real measurement, they can be hard. Yeah, for real, but it's honest. All right, and then if you want to measure resistance, you'll see it's not that different. The thing is you can't measure resistance if it's connected to the power source. So we need to disconnect it and you're going to measure, you could measure the whole circuit if you wanted. You'd have to disconnect here and disconnect here and then measure the whole thing. But for now, if we just want to measure the dimmer, we'll disconnect the dimmer from the circuit and we'll put on resistance and we'll just send our own electrons through the dimmer. The thing is, when you're measuring resistance, we're using our little 9-volt battery in the meter. Your 9-volt battery is sending electrons out. If you're still connected to the 12-volt battery, you're going to get like a negative ohms reading. And if you see a negative ohms reading, you're like, not only does it have no resistance, it's almost like it's extra electrons are making it. Yeah, that's because it's still connected to the power source. So that's your chance to correct. You didn't hurt the meter, you just got a bad measurement, misdiagnosed the car. So not a real big deal. Okay, and then we will summarize with parallel and series parallel. They're not really that crazy. I think if you understand series like we talked about, and voltage drops, I don't think this would be that hard. So in a parallel circuit, all the components are connected directly to the voltage supply. Interesting. All right, so like the way that I would relate that is old school Christmas lights. They were in series, and if one bulb blew, all the lights went out. And then you're over there like, is it this bulb? And you undo a bulb and you put a test bulb in. Nope. Is it the next bulb? And you undo the bulb and you put a test bulb in. Well, that was very frustrating. So a lot of the new Christmas lights are more like parallel. If one bulb blows, all the other bulbs still work and you just keep using them. Make sense? So in parallel, they have their own connection to the power supply. So if one load fails, the other ones will keep working, basically is what it's saying. All right. And then if you look, here's what that looks like, okay? The picture is going to tell you everything you know. Remember, this is how series was. If this bulb is blown, this bulb won't work either. But if this bulb is blown in a parallel, this bulb will still work because look, they both have their own supply to the battery. Make sense? It's kind of like a 2-lane road. If you got a 2-lane road and one lane is shut down, it's not going to stop the other lane. Make sense? So the way that we troubleshoot these is it's just a little bit different. If it was a series circuit and the 2 bulbs didn't work, I have no idea where the defect is. The defect could be here, 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 here. I have no idea. I have to go measure everything. If it's a series circuit, follow me. If both bulbs are not working, where do we suspect the defect is? You think you got 2 bad bulbs?
No, it's the battery.
Somewhere, I would suspect, I agree with you, you're following pretty well. I would suspect most likely between here and here. And why specifically here?
Because the source voltage is going to both of them.
Right, so if the problem was here, what would happen? This one would stop. But if they're both not working, it's probably in this part. In a way, sometimes we call this the series part, but it's not technically true because I guess it is, but a lot of times we don't really consider this to be a series parallel. And it's kind of weird because when I look at this, I look at like, hey, that's kind of like a series parallel. It starts off in series and then it goes to parallel. But the reason it's not a series parallel is because we don't have a load down here. So we don't consider it a series parallel. If we had a load down here, it'd be a series parallel, but it doesn't. So this is just a parallel. All the parallel circuits have some part that's kind of like series first. Make sense? All right, so real world application. If you rolled up to the car and none of the tail lights worked, or let's make it brake lights. None of the brake lights worked. Could it be a bad left rear brake light bulb, right rear brake light bulb, and the two center high mounted brake light bulbs? You got 4 bulbs out? It's possible. But do you think there's something a little more likely? It's probably in the circuit where it's more like series, right? So that would be like from the battery to the stop lamp fuse to the brake light switch and to where it tees off, right? So a lot of the things with diagnosing a parallel circuit is just determining, is it in that part of the circuit, or is it in that part of the circuit, or is it in that part of the circuit, right? So if it's going to be down here, both bulbs are not going to work. If one bulb is not working, are we going to check all this up in here? If one bulb's not working, it can't be this part. If this part's bad, both bulbs aren't working. Exactly. Exactly. So when we're diagnosing a parallel circuit, we really just break it down into individual series circuits. Okay, so if both bulbs are out, I'm in this area. If this bulb is out, I'm in this area. If this bulb works, but this bulb is out, I'm in from here to the ground area, right? So on the ASE, there's just basic questions like if both of these bulbs are out, technician A will say that it's that ground. And if you look at that diagram, that ground being bad wouldn't affect the other bulb, and both bulbs are out, so that technician is a no. Make sense? Like, it's actually really simple if you're following what I'm saying. Cool, so that's the main lesson on how we practically diagnose a parallel circuit. Now, of course, to be thorough, we're going to have to throw a little math in there. But again, there's a few laws you must know as well. In the parallel circuit, the voltage drop, the voltage across all branches are equal. Okay, so what it's saying is this is a branch, this is a branch. They're equal means they both get access to how much voltage? Yeah, they each get 12. Now that's different. Remember when in the series, the two siblings have to share the 12. You get 6 and I get 6. See, in a parallel, you get 12 and I get 12. Pretty cool, right? Sounds better. Better in a way, but different. Different if it fails. And then look, the total current in a parallel circuit equals the sum of the current flowing in each branch circuit. Let's talk about what that means. Let's say that we had, let's go with 6 ohms and 6 ohms. The total resistance would be like 12, and you'd have 1 amp flowing in all this whole thing. 1 amp here, 1 amp here, 1 amp here, 1 amp here. This is different, right? If you had, let's go with 6 ohms right here and 6 ohms right here, we don't calculate it in the same way. That would mean this gets 12 volts, and if it had 6 ohms, this is 2 amps. This gets 12 volts, and this is 6 ohms. It also gets 2 amps. Whereas the other ones with 6 and 6 was going to be 1 amp, this is going to be double because it's a second path. It's a second way for electrons to flow, right? So in practical application, the reason that's so critically different is in a series circuit, every bulb you add, you're actually adding resistance, you're lowering the amperage. If it's in a parallel circuit, it gets a little crazy because if you add a bulb, you're also adding another branch, which overall is actually lowering the total circuit resistance, so you're increasing the amps, right? So if it was a truck driver and the truck driver's like, hey, I got my cool truck and I want to add a bunch of lights, if they just start adding branches on branches on branches to put a bunch of lights on there, the original feed down here is now supporting many, many more bulbs. So you may have a lot of amp flow down here, maybe too much for these wires down here.
You just need to get a bigger wire just for that section.
Yeah. It's kind of like, I mean, our local and state governments are guilty of this. It's like they want to keep building homes and building neighborhoods and neighborhoods and neighborhoods and neighborhoods, right? They're building branches. But what's up with the freeway? The freeway is the same thing. You built up all these new branches, and now there's way too many cars trying to go on this freeway that hasn't been expanded. Make sense? So if you want to do it legit, if you want to add 2 more branches, you may very well have to double this wire size on the freeway to support that. Now, you could calculate it, though, and I'll show you the calculation. But that's the idea. If it's series, you can't just keep adding extra branches because you're going to increase the amps in this part. Okay, and then it's saying the total resistance of a parallel circuit decreases as more branches are added. That's kind of what I was saying, right? So these go together. The total current in a parallel circuit equals the sum of the current in each branch, right? So if we had 2 amps and 2 amps, that means this part here is 4 amps. Then it's saying here, at every time you add a new branch, that's going to lower the actual total resistance. You add branches, this is going to keep going up and up and up in how many amps it flows. Because overall, actually, it's having less and less resistance. Kind of different, right? So the total parallel circuit resistance will always be less than the lowest branch because you're giving it more pathways, so it's easier for the electrons to flow when you keep opening up a new branch. Kind of fun. And then if you look, a parallel circuit's voltage across each branch is the same as the other branches. Doesn't matter how many branches. So if we add 100 branches back here, doesn't matter. They all get 12 volts to the load. Now you can have different resistances on the load, and that'll affect the amperage right here, but it'll still all get 12 volts. Right? That's what's a little different. Okay, and then if you want to determine the current flow in each branch, you got to look at the resistance of that branch along with the voltage. So if you were ready to, let's say, determine this branch right here, all you need to know is, look, we've got 12 volts. Oh, if it's 12 volts and 12 ohms, isn't that 1 amp? Yeah, because we did the Ohm's law. This one also gets 12 volts because it's in parallel, right? So it gets its own 12-volt source. So if it's 12 volts and 6 ohms, it's 12 divided by 6, that's going to be 2 amps. And then this one gets 12 volts and it's only 2 ohms. So it's going to be 12 volts divided by 2, which equals 6 amps. So we have 1 amp, 2 amp, and 6 amps on this parallel circuit, but we only have 12, 12, and 12 volts. They all get 12 volts. They all just produce an individual number of amps. I kind of picture it like little roads, right? So if you all jump on the freeway and you get off this exit, and this exit has less resistance, you're going to go fast. And if this exit has a little bit more resistance, you can go kind of fast, but a little slower. And then if you get off this exit and there's a lot of resistance, you're going to go really slow. It's individually dependent on that particular path, though. If this one backs up a lot, it doesn't mean that this one's going to go slower, right? They're independent of each other. However, they all shared the same freeway right here. So if you had 1 amp, 2 amps, and 6 amps, 6, 7, 8, 9. I add 9 right here. That's where the 9 came from. All those electrons had to share the same freeway, so therefore, this would have to be the sum of the parallels. Make sense? Kind of, sort of? I think overall, we're probably fairly good on it. And on the ground side, the same. That's the other thing. If you aren't using a chassis ground, you got to remember your ground wire size has to be good for the return path as well. We get a little spoiled in automotive because generally what we'll do is we'll just land this thing in the chassis ground, and the chassis is so big so massive, it can handle all the electrons you could throw at it. We're not normally real worried about the ground, but if it's an event where you have to actually run wire to support the ground, you better make sure the wire size you use is good for the 9 amps or whatever the calculation is. Okay, you're getting there. Okay, now math time. Okay, we love math. You want to calculate the total resistance. And why? I don't know. Maybe you need to know how many amps are going to flow so that you can size your wire or something, right? So truth be told, I never do this. I actually had to brush up a little bit on this because I had an incorrect formula. But we'll go through it. Here's the formula. You got to take total resistance, resistance 1, 2, and 3, and you got to put ones over top of all of them. So 1 over your total resistance equals 1 over each of your individuals. So R1 being 2 ohms, we punch that in there. R2 being 60 ohms, we punch that in there. R3 being 3 ohms, we punch that one in there. And I don't remember how I got to that though. I think we just made it common denominators there. So the best way to do it is to put them in there and then try to get a common denominator, which was 12, right? So if you had 1 over 2, that's kind of hard to do that in a fraction. This is where the math gets kind of mathy, right? But if you had 1 over 2 and 1 over 6 and 1 over 3, the next logical step would be to get a common denominator. So 1 over 2 is equal to 6 over 12. No, it just happened to really be whatever a common denominator was. So if we look at these, well, I guess we could have done 6. I don't see why we absolutely had to do 12. Let me think of if we could have done 6. 1 over 6. Let me think about that.
Yeah, because your voltage is also 2 divided by 12 would be 6, so that's why you're 6 over 12 and
Nah, this isn't going to be volts because this has nothing really to do with volts. But if you wanted, there's another way you could do it. If you just ran your calculator to be 1 over x equals 1 over 2 plus 1 over 6 plus 1 over 3, you'd end up with this same number. But to make the math more simple, we used common denominators. 6 over 12 is the exact same as 1 over 2. And then 1 over 6 is the same as 2 over 12. 1 over 3 is the same as 4 over 12. So we just made these common denominators, and that way we could do 1 equals 6. Yeah, that is interesting. It's really fuzzy in my mind, to be honest with you. But if you can punch it into this formula, then you can do it. I don't remember the longhand to actually do this calculation, to be honest with you. But if I were to jump in a calculator, I could actually do 1 divided by x and actually type this in, you'd get it. So if we were to look at that, what do we think our number is? Whoops. 1 over, Interesting. One over RT equals. In fact, I actually, I've seen it done a couple different ways. I may link one in here just to show it. Let's take a quick look. Because I went over it and I kind of remembered, but I'm looking at it, I don't recall this part well enough. So we want to know the total resistance. It's going to be less than 2. It's 1. I think it's the 1 ohm. It could just be 1. Yeah. Okay. Yeah. All right. 1 ohm. It's a little bit of a weird calculation for me to remember. 1 ohm, because it's 6, 2, and 4 over 12. Hold that thought. It's going to be 1 ohm. See, there's the longhand way to do it, which is just it's not really something that technicians would do. Okay, so I'm just shooting. I'll be totally honest and vulnerable with you. It's really not something we do. I have done it. I just am blanking. So if you look, 1 over R total equals 1 divided by R1 plus R2 plus R3. So it'd be a way that you'd substitute those in. Or you'd use the shortcut. Resistance total equals R1 times R2 divided by R1 plus R2. But I don't remember how to do it if there's 3 of them. See if I can. Oh no, it's not a easy video, is it? I thought that would be pretty good. Yeah, let's run this one. I'm good with this. We gotta watch some ads first, okay? Apparently. Can I skip? There we go. All right. I'm doing no sound on purpose, FYI. All right. Hey, these are our numbers. Okay, there's the formula. Let's talk through it. All right, so let's pause here real quick. Okay, so these are our actual fractions, right? You guys follow those. How did we get 1 over 2? Because that's R1 is 2, R2 is 6, and R3 is 3. So we know how we got that. Agree with that. Okay. I may actually have to do a little sound. I gotta back up. I just don't recall why we did 12. So see, we picked 12 because it's a common denominator, but I think that, why couldn't we have done 6? But whatever, they picked 12 to make it a common denominator. I was pretty sure on that. Okay. Okay, now it's ringing a bell. I just was a little thrown off by the 12. I couldn't remember the 12. We came up with 12 just because they all go into 12 easily. Then if we make it a common denominator, 6 over 12, 2 over 12, 4 over 12, you add those all up. The total was 12 over 12, so that's 1. So you understand if it's 12, what's 12 over 12 equal to if it's 1 over? What would this number be? Yeah, 1 over 1 is the same as 12 over 12, and so that's why RT is 1. It's definitely fuzzy in my mind. I thought that I was going to remember it a little bit better than I did. So you guys can forgive me or call me a slacker. I'm good with both. But I'm also going to let you know I will not do that calculation with you again. And I also will not do that calculation until, guess when? Next time I teach this class. I don't, it's just, I'm telling you super real. Like technicians, we don't really do this. And that's not, probably not really a great excuse for me not to remember how to do it. But what we do is a little bit different. And so the whole purpose of knowing the math is so you understand how the electricity functions, not necessarily so that you can fix the car, right? So you're not likely to be doing this math to fix the car. If you're custom building something and making a harness and doing some electrical engineering stuff, yeah, you'd need to do that calculation. At which point, do you know what I would do for real? Watch the video again. And I do it. And then you know what I do after that? Forget it again. So I was looking at the time, and today we got just a little bit more to do, but it's not a ton more to do. So I think I'm going to do. All right. All right, so hopefully that answered that for you guys a little bit. Now, if you had to calculate total resistance, you could. But let's move on from there, since it's not my favorite subject. So we could discuss series as if the loads are in a series and the electrons have to go through each one of them consecutively. Now you know series, right? What if we were to discuss parallel? That's where if one branch is cut off, the other branches still function, right? Now we got a new one though. A series parallel, which it's not really new, it's just a combined, is a part where there's a load in series and then after that loads in parallel. So kind of the same but different. So like for example, if we are looking at this, let's trace this, comes off the positive, goes to the switch, goes to this load, that is just simply parallel. If we look, I do have a series parallel, but I actually have to back up for it. This is a series parallel. I fibbed in this, oh, it's actually not. I fibbed to you right there too. Dang it, I thought I had it and I must have missed it. No, it's not actually. But I can draw one in, that's okay. I'm gonna make this work and fix it. I was pretty sure that I had it though, but apparently not. So if I take this, although it's a good enough lesson because it looks like it's series parallel, because wouldn't you say this is the series? But it's only series if it has a load. So if I were to draw a bulb right there, now that would be a series parallel because there's a load in the series part. So if we were to do the series part traced, let's do it in this color, pink. This would be the series. And then let's pick a new color. Let's do, I don't know, like green. This would be parallel, and this would be parallel, right? So a true series parallel has a load in the series part and a load in the parallel part. It can actually be hard to find that as an example. There's only really one that I can think of with regularity. And that's, if you jump in the car, you know how you can dim all your interior lights or brighten them or dim them? That was like the only series parallel part, because this would be all your little lights, like the little backlighting on your instrument panel, your little radio lights, your power window, lights on the switch. This would not be a light bulb though, this would be a dimmer. So the reason that we'd want a series parallel is because we could use this to affect the available voltage to both of these, right? So if we were to draw that out, what would happen would be, let's say we started with 12, right? And then if you look at this part, we would drop some amount of voltage right here. So I'm going to give you some like really nice clean numbers. Let's say we had, let's go with a 6 ohms on the series part. And then let's just say we had a combined 6 ohms of everything over here. Everything this way was all 6 ohms combined. That would mean that you'd drop 6 volts right here, and then these would all drop the remaining 6 volts. So it's a little bit weird to think about, but you would understand it using Ohm's law. If these bulbs only got 6 volts, they're going to glow dim, right? So if you set your dimmer to 6 ohms, these would glow kind of dim. Then if you turned your dimmer up and you wanted the intensity to increase, maybe you drop it down to like 1 ohm, then these would get a higher voltage and they'd glow brighter. So we put a load in the series part that we can vary, and essentially it's just a dimmer. That's about the only time you're ever going to really see the series parallel. And we'll do a little bit of experiments on the series parallel, but there's no reason to go really nuts on the series parallel because it's so rare. But if you were to encounter one, you diagnose it the same as like a regular parallel. If you had all the bulbs having a problem, you'd expect it to be in the series portion. Or if you had these bulbs up here having a problem, you know it's related to this area, not this area, and not this area, right? So it's fairly logical. So if you do have a series parallel failure, you're just going to break it down into, is it a failure on the series part or is it a failure on the parallel part, and which branch of the parallel part if there is an issue there. The other thing, again, that we keep in mind that's same as a parallel is if you increase the current flow on one of the branches, it's going to increase the current flow on the series part. But that's the same as a parallel. So with that, not really that complex, I'd say. Now you know all the different types. And then when we talked about that Kirchhoff's law, it's saying all the voltage will drop across the circuit, but additionally, the current entering a junction is equal to the sum of the current flowing out of the junction. So what's that mean? This is a junction right here. Junction, right? So we have 12 volts going up to all these bulbs. We have each of the bulbs consuming the 12 volts. We have 0 volts going to the battery. But if you look at it in amps, it's a little bit different, right? So in a series, in a parallel circuit, they all have 12 volts. They have the same voltage available, but they'll flow different amps on each of the branches. So it's just, in this law, it's just saying, if you have 12 amps exiting the battery, that's going to be the sum of each of the individual branches. And then, of course, if you bring it all back into, after the junction into one path, it's going to be back to the sum, right? So you had 12 amps, 2 amps went here, 4 amps went here, 6 amps went here. And then if you really wanted to be kind of weird, if you think about it, 12 amps came up, 6 amps would have essentially like peeled off right here, which means right here would have 6 amps. Then another 4 amps peeled off and left, so technically you'd really only have 2 amps. This would be 2 amps right here. And then would be to 6 amps here, and then be to 12 amps here, right? So, I mean, it's fairly logical when you look at it and you think about it, but that's the Kirchhoff's law. So if you needed to do calculations because you're adding more and more branches, no problem, apply Kirchhoff's law. If you add an individual branch that has 12 volts and 12 ohms, that's going to be 1 amp by Ohm's law. applying Kirchhoff's law would be, well, we just added 1 amp, so therefore this is going to be 13 amps using Kirchhoff's law. That's it. So you probably need to run wire that's going to be good for over 15 amps and bump your fuse size up to 15 amps at this point. Kind of makes sense? Not that tough. All right, and that's generally what it tells. It kind of talks about the loop in a sense, right? Okay, so, and here's Kirchhoff's law applied in another helpful way, and this is a good way that we'd actually use to diagnose it. Kirchhoff's voltage law. Okay, here we've got point A. This is voltage, so not current anymore. Back here we're talking about Kirchhoff's current law. Kirchhoff's voltage law is actually the main way we're going to diagnose a problem with a circuit. Point A of the battery, we could measure, and then we could go to the next point in the circuit, point B, and we could determine how much voltage has dropped. And we're going to do that, but for now, just understand, you could measure A, and you could measure B, and you could do the math. So if you had 12.0 and 11.9, you'd know it dropped 0.1 volts. But in this case, we're just not even going to make you do the math. We're just going to say from A to B, it dropped 0.025. That was the voltage drop number 1. From B to C, it dropped 11.835. This example. Does that seem like a high voltage drop? 11.835? Is that bad? True, but is that bad? Why is it not bad? Yeah, that's what we want it to do. I mean, that's the light bulb, so shouldn't it drop that? We're trying to pay the light bulb. We're not really thrilled with having to pay anyone else. We're willing to pay 0.025 to the little connection and to the wire and to the fuse. But if we were to be dropping like 5, 6, 7, 8 volts over here, that'd be a big problem. We would expect to drop most of the load there, okay? Then as you continue, we drop another 0.025, another 0.06, another 0.03, another 0.025. If you were to add up all the voltage drops, what would you get? 12 volts, whatever the source was, right? So that's Kirchhoff's law, saying if you measure your battery and your battery is 12.0, by the time you build a complete circuit, your voltage drop sums will all come out to the total every time. That's it, period. Now that's very nice because that allows us where we can just come up and do, if we're just going to diagnose this, honestly, I would just voltage drop B to C. And if B to C was 11.835, like that's good. We're good. I don't really have to go through and voltage drop everything because that's acceptable. Now, if I were to voltage drop B to C and it were to be like 6 volts, I'd be like, wait a minute. Applying Kirchhoff's law, if I voltage drop 6 volts on the load, what's that tell me about the rest of the circuit?
There's something higher resistance somewhere.
True. So if it's dropping 6 on the load, how much is it dropping in the other parts of the circuit? Right. And you know that now. But we didn't measure that, but you know it because you applied Kirchhoff's law. So that's where this comes in kind of nice when we're diagnosing, is just, hey, let's measure the load. What's the load dropping? If it's a good number, we're chilling. We don't need to measure anything else. If it's a bad number, we're like, all right, I verified. There's a problem out in the circuit somewhere. We don't know if it's before or after, which is why, like for me, I'll switch over to available voltage and I'll be like, how much is the load getting? And if the load is only getting 6, I know it's before. But if the load is getting 12 and it's still leaving 6 afterwards, I know the problem is after. So at least I've split the circuit in half, and I know if I'm looking towards the front of the car, towards the back of the car, and just systematically diagnosing it, right? So this is like, what I would personally do. If you voltage dropped each of these and you found that there was incorrect voltage drop, I would switch over to the available voltage. I would predict the available voltage. If I went to go in before the load and I only had 7.1 volts, I'd be like, oh, clearly there's a voltage drop before the load. In this case, it happened to be that dimmer like I was giving you the example of in the series parallel. So applying these different laws is what's going to help you understand where the defect would be, right? And then there's just a summary of the measurements. Current in a series circuit is the same as how we measure every circuit. It just depends on what you want. So if you just want to know the current in the series, you're good right there. But if, let's say, and resistance, actually that was a little bit redundant, but let's say that we had our parallel circuit. If you want to measure current, it depends on where you want to measure it. If you want to measure the current of the total circuit, you'd have to break it open down here. But if you want to measure the current of, like, let's say just this branch, you'd have to break it open up here in this branch, right, to just give you a feel for kind of where we're going. And then where we're going to wrap it up today, because we are pretty much done. I just wanted to give you a break. I had to actually jump on a meeting, to be honest with you. Is a little preview. We want to go into symbols, and that's actually what we're going to do today. So you're going to do some service info stuff, and then I also want you to learn these symbols, but I'm not going to let you cheat and write it down now. But just know we're going to need to be familiar with some of these symbols when we get into Unit 3. And then shortly after that, when we get into Unit 5, you're going to have to look at a wiring diagram. So you need to be able to pull this material. So if you get a car that's got a defect or got an electrical problem or whatever, Kirchhoff's law and Ohm's law and these types of laws, you need to know it, but you need to get the specifics for that vehicle. And mostly that comes from a wiring diagram. So if you look at this wiring diagram, it doesn't give us any steps. It doesn't say, like, press the power door lock button and see if it gets 12 volts at terminal 1 and ground at terminal 2. It doesn't say that. But if you understand this well enough, and as we study wiring diagrams and you start to predict voltages, you should be able to come to that conclusion. And then the next step is where we get in there and we'll put the meter on there and interpret a reading. And when you interpret that reading, if it's a good reading, great. But if it's a bad reading, your fundamental understanding of electrical will be like, oh, I'm supposed to get 12 volts on terminal 1, but I'm only getting 6. That would tell me there's a voltage drop somewhere in the circuit because you know Kirchhoff's law. And you could even apply Ohm's law if you wanted to be like, well, that would mean, I'm going to get, if I've got half the amperage, I must have double the resistance, right? So sometimes we fall back on these electrical theories to be able to actually diagnose this. But this is what we're going to be doing now, is symbols and wiring diagrams, okay? So, got any questions? Now is